Graphics give a rough idea of roots for a function, but for many problems, it is preferable to have methods that come up with the correct answer automatically, usually iteratively. Potential solutions are calculated to see if it is the real solution. If not, then it is adjusted and calculated again until it is very close to the real solution. This procedure is called iteration, and the result of being very close to the real solution is called convergence. For those who would like to know more about details of terms introduced here, please refer to the textbook. Two major types of methods are the breaking methods and the open methods. Breaking method guarantees an answer but usually computes slower. And the open method acts quicker but does not guarantee convergence. Two major types of methods are the breaking methods and the open methods. Breaking methods guarantee an answer but usually compute slower. And open methods act quicker but does not guarantee convergence. For bracketing methods, there is an initial guess. Initial guess may naturally arise from the physical context you are analyzing. However, in other cases, good initial guesses may not be obvious. In such cases, automated approaches to obtain guesses would be useful. Now we start with an approach, the incremental search. Incremental search locates the brackets where the function changes signs. For example, in one end of the bracket xi, fxi is positive, and in another end of the bracket xj, fxj is negative. Then we can target at least one root between xi and xj. In this figure, x4 to x5 is an ideal bracket. However, there are potential problems regarding the size of the bracket. Some problems are shown in this figure, for example, bracket x0 to x1, where fx0 times fx1 is positive, and we might miss the two roots in this bracket. An extreme case with many roots is the bracket x2 to x3 in this figure. So if the incremental length or the size of the bracket is too large, we might miss roots within the large brackets. Here we share a piece of code, which is a function of incremental search. What it does is to recognize a function to be solved for roots, the interval starting with xmin and ending with xmax, and ns is the number of brackets the interval is to be split into. The sign of fk times fk plus 1 is examined to see if there are any brackets with changed signs. If yes, store those brackets as potential root locations. We will revisit this method later. This is an example calling the function that we just defined, which is incsearch. The first input of incsearch is the equation that we are trying to solve for roots. Here we use anonymous function in the format of @x, sine 10x plus cosine 3x. The second input is 3, which is the xmin, the starting point of the root search. The third input is 6, which is the xmax, the ending point of root search. Here we did not set the number of intervals, so it uses the default number of intervals, which is 50. Although 5 sign changes are detected, because the subintervals are too wide, the function misses possible roots at x equals 4.25 and 5.2. Each represents two real roots that are very close together. The function can be run again with more subintervals with the result that all 9 sign changes are located. Here we call incsearch again, but this time we set ns to be 100, which is 2 times the default. This gives us half the size of each bracket compared to the default. And this time we find all 9 intervals that contain roots. From this example, we can see that bracketing methods are in fact brute force, where small enough brackets can give all the roots. In the incremental search method, we divide the whole range evenly into the required number of brackets. Now we introduce another method called bisection, in which we utilize the midpoint to decide the brackets. If a function changes sign over an interval, the function value at the midpoint is evaluated, and the process is repeated until the root is known to be in the required precision. The location of the root is then determined as lying within the subinterval where the sign change occurs. Let's revisit the root solving example, which is fxi equals e to the power minus x minus x. The solution, first we calculate the first derivative, f prime x, which gives us minus e to the power minus x minus 1. And then we can calculate xi plus 1 to be xi minus e to the power minus xi over minus e to the minus xi minus 1. And the table shows in each iteration the xi value and the true percent relative error epsilon t. If we compare this table with what we can obtain from simple fixed point iteration method, which we introduced at the beginning of open method, you can see that the epsilon t decreases much faster at each iteration. This is the bisect function definition. There are several inputs. The first input, func, is the function fx to be solved with roots. xl and xu are the lower and upper boundaries for the guess. Es is the desired relative error. If Es is not in the input when calling the bisect function, it uses a default value of 0.0001. The fifth input, maxIt, is the maximum allowable iterations. If it is not in the input when calling the bisect function, it uses a default value of 50. P1 and P2 are additional optional input arguments for the function, which we do not cover in this course. There are several outputs. Root means the real root. Fx means the function value at the real root. Ea is the approximate relative error in percentage. ITER is the number of iterations used to achieve the result. In the body of the function, we use a while loop to keep the iteration going. XR is the newly calculated boundary position. It will be used to form the new bracket that contains the root. And in each iteration, error is calculated by its definition. This is the way to call bisect function to solve for the roots of fm equals 0. We call bisect by the command mass fx ea iter equals bisect fm 40 and 200, so that we can find the root of fm equals 0 in the range of 40 to 200. There is a MATLAB demo of defining bisect and calling it to solve the root problems. A result of m equals 142 kg is obtained after 21 iterations with an approximate relative error of epsilon a equals 0.00005345% and a function value fx close to 0. The third bracket method to be introduced today is the false position, also called linear interpolation method. In this method, we locate the root by joining the value of fxl and fxu with a straight line. The straight line intersects with x-axis at point xr, which can be calculated by the following equation. xr equals xu minus fxu times xl minus xu over fxl minus fxu. And we treat xr as the renewed root position because it's close to the real root, which is shown as the intersect of the blue curve and x-axis.